Welcome to the podcast, Medicine Untold, and come with me on a journey to the unexplored side of medicine, where we speak with rebel doctors, radical herbalists, unorthodox healers, and patients who have healed themselves. Explore the intersection between science and spirituality, and discover the power within you. I'm your host, Dr. Michelle Berkland, licensed naturopathic doctor, botanical alchemist, and practicing physician. Hello, everyone. Today, I am Dr. Michelle Berkland, and today we have Dr. Gerald Pollack with us today. So thank you so much for joining us.
My pleasure.
And I'm going to introduce you to our audience. So I'll read a little bit about your background so they can get a feel for what we will be talking about today. So Dr. Gerald Pollack maintains an active laboratory at the University of Washington in Seattle. He is the founding editor-in-chief of Water, a multidisciplinary research journal. He is the executive director of the Institute for Venture Science, the co-founder for the Fourth Phase Inc., and the founder for the annual conference on the physics, chemistry, and biology of water. Dr. Pollack has received numerous honors, including the Prigogine, I think I pronounced that right, the Prigogine Medal of Thermodynamics, the University of Washington Annual Faculty Lecture, the NIH Director's Transformative Research Award, and the first Dr. Emoto Peace Prize. He is recognized internationally as an accomplished speaker and author whose passion lies in searching the depths of natural truth. Dr. Pollack's award-winning books include The Fourth Phase of Water and Cells, Gels, and the Engines of Life. So welcome today.
Well, thank you, Michelle. I'm really happy to be here with you and happy to talk about all this stuff, which really moves me. So thank you.
Yeah, no, I can tell. And as a naturopathic physician, water is such a huge part of what we teach our patients. And I mean, it's the core of life. So I think this is going to be a really powerful interview today, too.
Well, thank you. I fully agree with you. You know, it's been, if you read any cell biology book or biochemistry book or anything of the ilk, usually the book opens by stating pretty much what you stated about water being really important, and then the rest of the book completely ignores it. And the mechanisms that are described are based on the presumption that water doesn't exist or water does nothing. It's merely a background carrier of the more important molecules of life, like the proteins and the nucleic acids and such. So we get the impression that all the water does is it's just a solvent. That's all. It doesn't do anything. But what we found challenges that notion in a big way.
Right. It really does. So kind of moving on to the first question is, how did you begin studying water? How did you find that path?
Oh, well, um, where where to start? Well, we had been engaged in studying the molecular mechanism of muscle contraction, and the mechanism that everybody has learned, everybody knows about, was put forth by a famous, ultra famous Nobel laureate, Sir Andrew Huxley, who was he had every distinction, not only a member of the famous Huxley family, but also president of the Royal Society, a master of Trinity College, Cambridge, knighted by the Queen, et cetera, et cetera. And when he walked into the room, there was a hush. It was like God has entered the room. And the work that we were doing challenged his theory because the results didn't fit. And so at that point, I did learn a little bit about the process of doing science and how paying homage to distinguished people carried a lot of weight, because we had the evidence that the theory didn't work, and but the people in the field, there was a tendency to cling to the ideas that he was espousing, because he was this distinguished man. So I was sort of open. I became open to alternative ideas, and And one day, as we were studying the muscle contraction, a colleague, I just picked him up from the airport, and I was driving him and his wife from the airport to my home where they were going to stay for until they could find a place to live in Seattle. This Hungarian guy, he tells me, you know, you should go to Hungary. There's going to be a symposium in Hungary. And the symposium was dedicated to the memory of a guy named a biophysicist named Ernst. And he was telling me Ernst had two passions. Uh, One was muscle contraction, and the other was water. And his ideas on muscle contraction pretty much conform to yours. He was telling me. He said he was convinced that Huxley's theory was all wet. It was just absolutely wrong. And he said, why don't you go and you can represent muscle? And at the same time, his interests were also in water. And there's a group of people coming to the conference to talk about water. So I say, why not? You know, I like Hungary. Take a trip to Hungary. And I hadn't realized what kind of impact my trip would make, because there I met a guy named Gilbert Ling, Ling, and a bunch of people who were going to present ideas that supported the views of Gilbert Ling. So who's Gilbert Ling? You probably never heard of Gilbert Ling. So um, Gilbert Ling came from China. He was chosen in the first cohort of people throughout all of China to come after World War II. It was 1948. By the way, he passed recently at age 100. So they looked all around China, and they looked for one person in physics, one chemistry, and one biology throughout all of China. So you can imagine these were top level people who had already achieved something and were going to be sent to the US to study in famous laboratories. And one of them, the physicist, C.N. Yang, won a Nobel Prize in physics. And he became even more famous for when he was in his 80s. He married his 30-year-old translator. So that was a lot of stuff that went around the press in China. But anyway, he won a Nobel Prize. The chemist was distinguished, and one of my Chinese students said he also won a Nobel Prize. I'm not sure. And Gilbert Ling should have won at least 2 Nobel Prizes like the others, because of what he was presenting. So his idea, which moved me, which had a big impact on me, the question was, how did I get involved with water? He said that water in the cell was not the same as water in a glass. So water in the glass, you know, the molecules are dancing around, randomly oriented, dancing at a furious rate. And Gilbert Ling said, no, in the cell, the water is different. He said the molecules are actually lined up like soldiers at attention. They're organized. He called it structured water. And he presented evidence that really that was really convincing to me. And he'd already written 3 or 4 books on the subject. And then other people came and presented evidence that were consistent with his point of view. And I'm thinking about it, and I consider myself a little bit naive, and sometimes I'm deluded by fancy presentations and such. So I was really mesmerized by this stuff. And in order to check myself out, I took one of his books and I gave it to a few of my students. And I said, hey, what do you think of this stuff? For me, it was so compelling that I had this urge to get into the subject myself. And they came back to me and they all had the same opinion. Yeah, this looks not only like it has the ring of truth to it, but it's profound, because if it's right, everything else is wrong. Everything else in biology. In other words, if the molecules were lined up, that he was saying that they were lined up like each water molecule is a dipole, like a bean with plus at one end, minus at one end. And so you can imagine that they could stack. Minus next to plus. And Gilbert argued that they could stack for long distances. And the evidence presented not only by him, but by others it was really compelling. So when my students reaffirmed what I believed, I said to myself, I got to do something about this. You know, we've been studying muscle contraction, trying to make headway, and we made some, but mostly the Huxley name was so dominant that it was just impossible to break through that barrier, which was okay because I did learn something about doing science and what matters and what doesn't matter and the human aspects of it. So I decided to get in. We had no money to study water. We had some money to study muscles. And so I decided the first thing I was going to do is write a book. And I did. It's called Cells, Gels, and the Engines of Life, published in 2001. Um, and the book made an attempt to describe Gilbert Ling's idea and evidence in a way that was approachable to non-experts. You know, because Gilbert Ling had a habit. I'm not sure if this is exactly accurate, but I think he'd sit down at the word processor or at a typewriter before that. He'd bat out something and he'd send it to the publisher, and the publisher would publish it. And Gilbert Ling could understand it, but other people had a devil of a time figuring out what he was trying to say. And I came to a sort of a conclusion that maybe in the Chinese language, maybe the word editing is absent. I'm not sure, but I don't think he ever put his stuff through an editor. You really had to scratch your head as you were pouring through it to get it. Anyway, I'm not sure I got it all, but I made an attempt, and the book it was how I sort of broke into it, and the book got mixed reviews. Some reviews said, "Oh, pay no attention to this book because it's just more of Gilbert Ling." And everybody knows that Gilbert Ling is a crackpot because he's he's saying that the water in the cell is a different kind of water. It's more like a crystal or a liquid crystal or something, and makes no sense. Therefore, forget this book. On the other hand, there were some really positive reviews, and one guy from Harvard, well-known cell biologist, wrote that, quote, "This is a 304-page preface to the future of cell biology." I like that one better. So, so anyway, eventually, or soon after, we got some money, and then we started in doing experiments. So, just a kind of addendum to what I've said is that all along I thought something not only was wrong with the accepted model about how muscles contract, the Huxley model, but there was something that I had an Israeli guy in the lab. His name was Reuven Tirosh, and he kept telling me water is important. Water is important. He had his own theory about how water could produce muscle contraction. And I must admit, at the time, it was early on. I didn't pay so much attention, but the central theme struck me that water is important. And if anybody looks at the mechanism of muscle contraction that you could read in textbooks, water is not mentioned. So it's as though the proteins that undergo conformational changes to produce the contraction, they work in a vacuum. They don't work in water, but they do work in water. And so there's a disconnect between what's proposed and reality, because if something works in water, it's not the same as working in a vacuum. And so this guy, Tirosh, he made an impression on me, and I had in back of my mind that water must be important in muscle contraction and probably in everything that the cell does. So I got interested in, yeah, I mean, I was particularly open to the idea when I went to Hungary to this conference that, yeah, water is really important. And I was totally moved by Gilbert Ling and by various colleagues who supported it. And so eventually we started doing experiments, and what we found to some extent confirmed Gilbert Ling's ideas about the structure of water that's in the cell, but in other ways didn't confirm. We had some observations that differed from what he was talking about, and they're really important, very important. And so there we are. That's how I'm sorry for the long discourse, but you asked, and so I answered.
No, I think that's great. And it's interesting how you kind of began your career in research. It was like, it was a blessing in a way for you to confront these issues very early on of, hey, this might not be the way for this route, and questioning Huxley, because I think that gave you so much insight into thinking differently too, and understanding all the flaws in science and biases and different things on how to navigate that kind of early on too.
I did absolutely, and I got to tell you an anecdote. I'm sorry, I'm not strictly adhering to question and answer, but um, we early on in my career, I had some really brilliant people in my lab, and we did experiments. We had three different experiments that didn't agree with Huxley's theory, and I'd never met Huxley before. I just heard, he's a legend, and I thought, okay, I got to meet the guy, and so I went to London, and I distinctly remember I had an appointment in the morning, and I arrived 30 minutes early. So I sat on a bench outside thinking, what am I going to say to this, legendary guy? Who am I? Young scientist, freshly minted, and we have some evidence, but how am I going to treat this famous guy? And I was a bit intimidated, I must admit. So I went and I met him, and he treated me in a cordial way. Um, and um, so sit down, please. Tell me about your experiments. I understand you have some data that doesn't agree with the theory that I proposed. And so I went through, and he asked numerous questions about the data. How did you do this? How did you get this? Et cetera, et cetera, et cetera. Genuine questions. And then after 3 hours of that, and it was really serious, and he was really into it. He really wanted to know what we found, and he would never quite admit that, yeah, this my theory doesn't, or your evidence doesn't fit my theory. He never quite said that, but it was all over in 3 hours. He turned around in his chair and reached into a cabinet just behind him, and he pulled out a bottle of sherry. He poured glasses of sherry, and we had a drink together. And it was then that I realized uh, that this poor guy, this poor famous guy, sort of like the British monarchy, sitting in an ivory tower, and he's so important that nobody would ever challenge him. I challenged him. He loved it because the guy was an intellectual, even though we had evidence that his theory didn't make sense. I mean, it wasn't. It was an. I still think it's a non-starter. It just simply doesn't work for various reasons that we don't need to get into right now. But the poor guy, I felt the poor guy was so isolated. When you're like the king, nobody nobody goes to you and challenges you, right? Because you're the king,
Hmm.
you're the queen, or whatever. And he was in such an exalted position that his position was not so different from being a member of royalty. In essence, he was royalty. So I learned something from that experience. I learned that some of those people who are elevated, they pee in the same pot, and they eat the same food, and they make love in the same way. They're just humans, and and that poor guy was so isolated from the world. So there you go.
Yeah. No, that was great that you had that opportunity too, to
I
meet with
it
him
was
and sit down and go through it.
it was great, and we sort of maintained a friendship, if you will, throughout his life, or as long as I was in the muscle contraction field. His wife even sent Christmas cards to my wife, and we'd meet at meetings. And the truth is, I would avoid him. I just didn't know what to say to the guy, um, and we attended a lot of the same conferences, and he even came to Seattle for a visit, and I didn't know how am I going to entertain this guy, and
Mhm.
somehow I managed. Uh, I arranged cocktail parties and stuff like that, and he told me before he arrived, he said, "I've got lots of cocktail parties in London. I don't need more cocktail parties. I want to discuss science." And it was real. He did, and so I rearranged what we were planning to do to accommodate his wishes. A nice man. It's just that I had nothing to say to the guy.
Yeah.
It's like Republicans and Democrats getting
Mhm.
together today.
Mhm.
They don't know what to say to one another.
Right. But yeah, I mean, he appreciated that and respected that from you. So,
Well, I'm not. I think he did. I'm not sure, but there was always kind of a modicum of respect that I
mhm.
could sense that he had for what we were about and what we were doing. But anyway, that's how um, I mean, I started in the contraction of muscles, and right now that's ancient history for me. And we moved into water big time. Um, so so that's how I started.
Okay, I'll ask the next question because I bet our listeners really kind of want to understand this. For the people watching this podcast and haven't researched your work, can you explain to them, like kind of on a simplistic level, what is the fourth phase of water and the easy zone?
Yeah, sure. Everything I do is simplistic, so I don't have any problem with that. Sophistication is usually beyond me. I keep it simple. Okay, so it's best to talk about this sort of chronologically, um, and to get the essence of what we've accomplished, what it might mean. So at first, I took my cues from Gilbert Ling. He said the molecules were all lined up, uh, and the water molecules, and so it's like a crystal, and and when you build a crystal, in order to get the crystal starts with some material that eventually becomes a crystal, and that material may not be pure; it may have impurities in it, and so in order to build a pure crystal, somehow the impurities need to be excluded, and so in trying to follow up Gilbert Ling's ideas is where we started. I'm thinking that what we should look for is some region of water that tends to exclude, because in order to build up this liquid crystal, the original water has to exclude stuff. So we set up a situation where we put stuff that ought to be excluded if it was building this structured water. So we started with we had a little chamber, and in the chamber we filled it with water and little particles that we hope might be excluded. And there are little spheres called microspheres, and they're widely used in science. And into the chamber we plunked a tiny piece of gel. Uh, um, and just like Jello or something. But we didn't use that. It was a polyvinyl alcohol gel, but it doesn't matter. And we put it in, and so we looked to see whether somehow in this system there was some water that would tend to exclude. Uh, and we found it quickly. So next to every surface of the gel was originally water to start with, but we looked in the microscope, it was water with the particles suspended. We looked in the microscope and we could see that the particles were being excluded from the water region next to the gel. And and after 5 or 10 minutes, um, this zone of exclusion, which had no microspheres, and everything else had filled with microspheres, but that region, about 2/10 of at first we found 2/10 of a millimeter. You could see it with your naked eye. Um, Profound exclusion. It was clear, and the rest of it had lots of microspheres. So that's when we began calling it the exclusion zone, because it excluded, and that was convenient because exclusion zone, easy to remember, but it doesn't work in Europe because it's dead and other places. But later we realized that's an inappropriate um, definition, but it's so easy, so to speak, that we hung on to it. But later we found that this zone of water had properties vastly different from ordinary liquid water. Every property we tried and succeeded in measuring, and a few other people too, the properties differed. And so because it appeared to be a different phase of water, and we thought at the time, yes, it does involve some kind of water ordering. So we called it looked like an ordered phase of water, and we called it the fourth phase of water, because none of the three phases had any properties that resemble that, and yet we had lots of experimental evidence that this was something different. So far, we're in agreement with Gilbert-Ling. Um, where we diverged from his point of view, and I think in a really important way, was when we started using electrodes. You know, I did my undergraduate work in electrical engineering, so electrodes and measuring electrical stuff was really important. I can't remember why we decided to do that, but we decided to measure to see if anything interesting occurred in this exclusion zone. And we used electrodes they're glass electrodes that come to a very fine tip, and it's filled with a solution of 3 molar KCl, potassium chloride, and invented, by the way, by the same Gilbert-Ling, who used it, and we use it too, to penetrate cells, to look at the cell's electrical potential. So we had lots of experience doing it, as did many people half a century ago. And we decided to use them to poke into the exclusion zone and, you know, see if we've found something interesting. We were shocked, so to speak, with the electrical measurements. And we were shocked to find that the electrical potential was not zero, which would be characteristic of ordinary water, but had negative electrical potential up to a couple of hundred millivolts. And we were shocked because this didn't make sense to us, because the whole system started with water, which is neutral. So how do you start with neutral water and you get a zone that has negative electrical charge? The only way that that could happen is if there's another zone with positive charge, right? Because the two have to add up to give you what you started with, which was zero, neutral, right? And we quickly found it. So we found the exclusion zone is negatively charged. So you've got a gel sitting here, and next to the gel was an exclusion zone that was negatively charged. And beyond that zone was water, or the water that you started with, but we measured, turned out that had positive charge. The positive charges were essentially dissolved in the water. And the positive charge that would come from the original water would be protons, H plus, just like in acids. But it's well known that as soon as a proton is created, if it's in water, the proton will join a water molecule to give you a so-called hydronium ion. So those positive charges, the positive charges were not bare protons, they were all hydronium ions. So you've got negative charge in EZ, and you've got hydronium ions outside. So what is that? It's a battery. So we found that 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 you started with pure water, and in the right circumstance, you get a battery. And batteries are capable of delivering energy. All right, that's what they do for a living. They generate electrical energy. So there we were, and not long after, one of the students, actually two different students, they stuck electrodes in the positive and the negative and the positive, and they could get electrical current, enough current to light an LED lamp. And so that was proof of principle that we really do have this battery here, and the battery contained energy that was deliverable. So that was cool, but it raised the question, which a lot of people, especially in the field of photosynthesis, and I don't want to deviate too far from the main theme, but the question, see, the first step of photosynthesis, let me defer that for later. Okay, but here's the question. If you got negative in EZ and you got positive outside, you know, it's sort of like man and woman, they want to come together, right? Plus and minus. But if you have a battery like this, something prevents the two from coming together, right? Because otherwise they want to immediately recombine. But you know, they're not recombining. So what is that? And that took a bit of head scratching to figure out. But So we wound up with a real understanding of what's going on and what's absolutely necessary. And that is when the EZ forms, it has a structure that's so dense that it doesn't allow those hydronium ions to penetrate back. The positive hydronium ions want desperately to recombine with the negative EZ, but the negative EZ resists because its structure is too dense. Its structure, we found, we were able to deduce, consists of, it starts at the surface of the gel or polymer or whatever is nucleating the growth. And you got the first sheet layer, and that sheet nucleates the growth of the second sheet and the third sheet, and the sheets keep growing, giving you that, as I said, to start with 0.2 of a millimeter, but we've been able to find up to a millimeter, even beyond in certain circumstances. So, and each sheet, the structure of each sheet is a honeycomb. So it's got hexagons. Now, in order to penetrate into the EZ, you have to go through those through the openings in the hexagons. Those openings are very small. And also, successive sheets are shifted by half of the hexagon dimension. So it makes the actual opening even smaller than that. Meanwhile, you've got hydronium ions here, which are much bigger than protons, and they simply are too big to enter into that EZ lattice, so they remain separated. Um, and and for any system like photosynthesis, for example, the first step involves the separation of charge and water, just like I'm talking about. And what hasn't been addressed is how they remain separated. They need to remain separated in order for all the subsequent steps to take place. But there's been no discussion of how they're kept separated. And therefore, I think that mechanism is maybe a special case of what we've found in the laboratory. And there's one further point, an important one that links the two even better. So, you know, photosynthesis is run by light. Light, first step of photosynthesis, light separates water into H plus, OH minus. I think it separates them into EZ and the positive region beyond the EZ. But in photosynthesis, it's light that's responsible for supplying the energy. And so if we put that aside for the moment, and what about the EZ? Creating a battery, you can't create a battery without energy, because a battery contains potential energy, which can be delivered, as I mentioned before, but you can't create that kind of energy from nothing. The only way you can create that kind of energy is to start with another kind of energy and then convert it to a different kind of energy. It's a fundamental law of physics. I'm not fond of accepting laws in physics until they're really sure they're right, but this is one that really does make sense. So, so you need another kind of energy to separate the charges EZ and beyond. And we found that that is light. It was a student who found that, who was setting up a chamber, and I guess he was bored or something, or curious. He took a gooseneck lamp that was sitting next to his setup, and he shined the gooseneck lamp, and he saw the exclusion zone, and the region that was illuminated, he saw the exclusion zone growing. And he ran into my office, he called me, hey, I found something interesting, and I saw it, and then we started doing real experiments, because we were wondering if, you know, it didn't take a rocket scientist to figure out that light, photons, energy is being put in, and that's the energy that's creating the battery. It's charging the battery, because obviously the EZ was growing. So we checked to see which wavelengths were important, and we studied wavelengths ranging at the short end, ultraviolet, and then longer into the visible spectral range, and then longer to the infrared range. And we found that the first two didn't matter at all, pretty much. Only infrared range. We say infrared light. It's pretty much the same as visible light, except a longer wavelength that our eyes can't detect. You know, but the same ilk. So And we found that it has extreme power, that even a very tiny, weak LED lamp can expand the exclusion zone, we found, up to 10 times. So you needed only a little bit of infrared light to give you a lot of energy to charge this battery. And I think it's kind of the same for photosynthesis. People talk about a couple of visible wavelengths that are important in photosynthesis. But if you bear in mind that it's the springtime, it's now that photosynthesis begins in earnest, because the weather's getting warmer. The weather gets warmer, it means there's more infrared energy, because infrared and warmth are pretty much closely correlated. They're not exactly the same, but pretty much. It's like if you put down the toaster and you look at the coils glowing, they produce heat and they're glowing. You say infrared energy is coming out, infrared radiation. Physicists would say infrared light. Um, and that's when photosynthesis gets going in earnest. In the springtime, that's when the leaves come out. That's when things begin happening. So photosynthesis, the first step, it must be sensitive to infrared light, just like we found in other systems that grow infrared, that grow EZ. It's the infrared light that is primarily responsible. So the bottom line, uh, the bottom line is, I think photosynthesis, the first step of photosynthesis, all of agriculture basically, follows the same paradigm that we found in photosynthesis. First step might be nature's version of what we found more generically. And of course, nature does it in the most effective and efficient way. So uses not only infrared light, but also other members of the spectrum to power it. So okay, to summarize, I'm sorry, I've gone on and on and on, but the properties that we measured, we found it's not just stacked water molecules that Gilbert Ling found. We found it's actually a transformation that occurs at a hydrophilic, needs to be hydrophilic boundary next to water that catalyzes, nucleates, whatever word you want to use, the growth of EZ and the positive charge beyond it, creates a battery from which you can get energy. And what charges that battery is infrared light. So I'm sorry, again, long answer to a short question.
And that wasn't really a short question. So I think that was a great answer. So, okay, so we kind of have a foundation now for what EZ is. And since we are made of water and we have it in all of our cells, so how does that affect us? How is EZ in our cells versus regular water, and how does that affect us?
In a profound way. Okay.
I know
So
that's a tough question to ask, but I think it'll help tie it in too.
no, that's the right question to ask, of course. Yeah. So what does this water have to do with the cell? And the short answer, and I'll expound on that in a moment. The short answer is that the cell is filled with EZ water. Um, and as you know, um, excuse me, if you stick an electrode into a cell, you'll measure negative electrical potential. Somehow the cell is negatively charged. And then so that's an assertion on my part that the cell is filled with EZ water. And if I'm right, and there's a lot of evidence that actually supports that point of view, you'll think, well, if the cell is filled with negatively charged EZ water, it must be negatively charged. If you stick an electrode in the cell, you'll measure negative charge, right? I mean, you take a paper bag and you fill it with negatively charged stuff, and you stick an electrode in, and of course you measure negative charge. That's not the way cell biologists look at it. Cell biologists look at it a different way. That's, I must admit, far more complicated. And I'll deal with that complication now because it's really, really important. So the idea arose more than 50 years ago, and continuing on, accepted by almost every cell biologist to this day, that the reason the cell has negative electrical charge has nothing to do with easy water, because nobody knew about easy water at the time these ideas came into being. And but they did measure negative charge. And so what's responsible for the negative charge? Well, it seemed reasonable that people at the time, 50 years ago, knew that outside the cell was high sodium, inside the cell was high potassium. And so the idea arose, well, there must be a pump in the membrane that pumps the sodium out and pumps the potassium in. And that's must be how it works. And there was a lot of research whose results seemed compatible with that idea. And the idea has expanded to the point where now the number of pumps that are needed to explain what's inside and what's outside the cell. Um, if you look on Wikipedia, I think it says more than 200. If you ask a former student who's in that field, it's over 1,000. Now, what's the problem with that? Well, the problem is you can't see it on electron micrographs. You expect to see these membrane gadgets strewn all about, but all you find is a continuous membrane that has nothing. You can't see this. That's the first problem. The second problem, approached by Gilbert Ling, was, pumps need energy to pump for pumping. And Gilbert Ling did experiments and found that in the most generous conditions, allowing everything in favor of the pumping people, that the cell simply didn't have nearly enough energy to pump the sodium out. And now there are 1,000 pumps, or some large number. And so the amount of energy that would be needed is simply extraordinary. So that's for pumps. And then not only pumps, but channels, ion selective channels were invoked, invented, thought to be, and they also thought to populate the membrane. And the reason for them is there were certain other ions or substances that were more inside the cell than outside, or more outside than inside. So how did they get there? Well, and the idea of ion selective channels came into being. And some of the same problems exist with those channels. I'll just cite one of them because there are many. I've written about this. The idea is you have an ion selective channel, and the channel pops open and it lets a certain ion through and nothing else, only that ion, and then it closes again. And if you measure the current that goes from outside to inside the cell, you can see a pulse and then another pulse and another pulse. And it seems that seemed to be really compelling evidence that there was a channel, and the channel was popping open and closed, giving you those pulses. A problem with that is you can take a synthetic membrane with no pumps, no channels, nothing, and you get the same result, repeated by half dozen different laboratories. That's only one of numerous issues that befall this theory. So I think the theory is wrong, although it's believed and accepted by probably close to 100% of cell biologists. I think it's wrong. And a simpler explanation is that you don't have these numerous pumps and equally numerous channels in the membrane. You discover a channel, you get a Nobel Prize. So there's a lot of incentive to discover a new pump or a new channel, and the number piles up. So a simpler idea is that the reason the cell has negative charge is easy water has negative charge, and the cell is filled with easy water. Very simple. So that's the tangent and the deviation. So that I wanted to make, and I think it's really important. It's one example of going back really and looking at the evidence, even though in cases where people are the belief system is so well entrenched. You really need to look at the original evidence and see if what is being believed is really true, because it's very easy for scientists to accept the mainstream point of view. It's easy to get funding that way for your research. And if you challenge that, then you have real obstacles, because often the people who will review your application for money are the people you're challenging. So the system doesn't work in that sense. So anyway, back to easy and what it does. Now, so you've got the cell is filled with easy water. Now, easy water is structured, right? It's organized. It seems that can't do anything. It's sort of like ice, but it's not ice. The structure is actually not so different from ice, but it's not ice. And it's sort of gel-like, and you can intuit the gel-like consistency in a couple of ways. One way, if you're brave enough, you take a razor blade and take your forearm and cut. So, what comes out? Well, blood comes out, obviously, but you'd expect if the cell is filled with liquid water, that the water would come pouring out like it would from a breached water pipe, but it doesn't come out. And even deep in your body, I got some surgeon friends, and they tell me you take a scalpel and you cut through the belly of a mussel, and if the mussel contained liquid water, the water would come pouring out, but they never see water come pouring out. So it's more, it's not a liquid, and the fact that it's a gel has been well known for almost 100 years, um, uh, and you could demonstrate that to yourself. You just take a raw egg, and you've done that. You've cracked open a raw egg, and the egg white is the cytoplasm of the egg cell, right? And it's not a liquid; it's a gel, right? So this gel, the gel-like consistency is exactly what you expect from easy water. Um, and that's why if you cut the cell, the gel-like consistency is one. It's going to say it won't come pouring out because it sticks to the surface. The egg white tends to be somewhat sticky, and so the interior of the cell is much different from what the cell biology um, school teaches us. Simply doesn't fit. And so what about that? How can things happen inside the cell? Well, the way things happen, and this is discussed in detail in my first book. We haven't talked about the second book. We'll get to it, the fourth phase of water, which is actually really popular. But excuse me, in the first book, and so the second half of the first book, the first half talks about Gilbert Ling and his ideas. The second half talks about how the cell might function with the idea that the water is structured, even though we didn't know at that time all the details that I've divulged to you and described elsewhere. So we made an attempt, or I made an attempt to do that, and I brought forth from the literature evidence that what happens in the cell is when the cell is in the so-called inactivated condition, like if you have a muscle cell, it's not contracting. If you have a secretory cell, it's not secreting. If you have a nerve cell, it's not conducting. It's the intervening phase, and that phase is filled with structured, or we say easy or fourth phase water. Everything is organized, and not much can happen because the cell, it's like it's filled with ice, and if you want action to occur, there's not much action that occurs in ice. But what happens as soon as the cell is activated to do what it's designed to do, so to speak, it undergoes a transition. It's called a phase transition. It's well known in physical chemistry, but not so much in biology. And everything in the cell changes. The water changes. It goes from EZ, or fourth phase water. At the time, I used the term structured water. It goes to ordinary liquid water. And that's when the action happens. The transition is to liquid water, and also as soon as it changes to liquid water, all the proteins can undergo their necessary conformational change to produce what the cell is designed to produce or designed to do. And then when it's all over, it reverts back to the structured state, to easy water, to proteins that are returned from their conformationally changed structure back to their original extended structure. That's the cycle, and I adduced evidence to support the idea that, or the view that occurred in a half dozen of the most common cells that exist, and presumably in other cells too, that there's not enough evidence, or we didn't have a chance to to explore. So it's during this transition phase that the cell is the water in the cell is ordinary water, that diffusion can occur, things can move around, hormones can enter the cell, waste products can be expelled from the cell, and what have you. So, and then it returns again, and the return is the energy requiring state, because the buildup of easy water requires energy. You see, and that's where, for example, infrared energy comes into play, because infrared energy is not coming only from your toaster or your electric oven. It's everywhere. Um, and the way you can demonstrate that is you can, in your room where you are now with the tulips, I think they are behind you.
Mm.
Is that what they are? We have them growing here too now, this time of year. But you turn off all the lights, and so we see nothing. You can see nothing with your eye, and your trusty cell phone camera can't record anything. It's like pitch black. But if you take out an infrared camera, that is just like your regular camera, but the sensor, instead of being sensitive to visible light, it's sensitive to infrared light. It'll record everything. I'd be able to see those tulips behind you, and the vase, and what's hanging on your wall, and the throw pillows on your sofa, and all. And because I can see them with the infrared camera, it means they must be generating infrared light, or uh, releasing infrared light or infrared energy. And so you've got infrared all around you. It's coming from everywhere. Of course, the sun is the most powerful, but it's coming from everywhere. And so it means that the energy that you need to build easy water it exists all around. And by the way, that's why the military uses it for a night light. They want to see the enemy's tanks. It's dark, it's nighttime. They whip out their infrared telescope or camera or whatever they use, and they can see what you ordinarily can't see. So everything is generating infrared light or energy. And so the cell makes use of that. When it returns, needs to return to the initial state, the structured state, which means build up or rebuilding easy water. And because the infrared light is all around us, and it's also coming from the core of our bodies, because metabolism is occurring, it generates heat, and the heat is essentially the same as infrared. So you've got energy you have coming from outside and coming from inside to restore what needs to occur. And the last point to that is, for cell action, you need this easy water, because if it's really true, what I believe is true from what we've explored and written in that book, then in order to undergo this phase transition, easy to liquid water and back to easy, the easy must be there. And if you don't have enough easy, then the full transformation can't take place, and your cells are dysfunctional. And if you want it to be functional again, what you need to do is restore the content of EZ. And there are various ways to do that. I can talk about them if you like. They're simple expedients that require not much in the way of almost anything. And evidence has shown that these expedients really do restore health. And I think the way they restore health is by building EZ. So maybe I'll stop there and wait for further questions. Yeah.
Yeah, I think that's the most powerful statement for everyone listening, that basically what you're saying is EZ is where the energy comes from in the cell, and a healthy cell has more EZ in it, so it can operate optimally.
Yes, that's exactly what I'm
So,
saying. Thank you for reiterating. Yeah, that is critically important. Yeah.
so I guess, yeah, the question is, if EZ is kind of the core of our health and the core of the cellular health that we have, how can we generate it in our own bodies?
Okay, so I'll tell you briefly a half dozen different ways that that if I can remember them, a half dozen different ways. So one of them is by drinking a lot of water, which I don't do because I like to drink coffee too much, but it does contain water. Mm. If you imbibe water, and everybody knows we need to be hydrated, but people don't understand exactly what is hydration. So we take in water and we pee out water also, but some of the water that we drink goes into hydration. And what happens is some of the water, not all of it, some of the water gets converted by our body in the presence of infrared energy, gets converted into easy water. So drink a lot of water, builds easy water in our cells, and we're healthier. And we know that, if you play 2 rounds of tennis, 2 matches, you're dead to the world. You sit down, you drink a liter of water, and you're feeling better already. Okay, so that's one first expedient. I'll let you keep track. There are at least 6 that I can think. Another one is to do for your hydration, to do juicing, and to go to your backyard and your garden, and pick some leaves, squeeze the hell out of them, and you're basically squeezing out the water. And what is that liquid that you're squeezing out? Well, the liquid is the interior of the plant cells. And these are freshly grown plants. They're full of easy water. The inside of the plant cell is just like our cells should be. It's filled with easy water. You're squeezing out easy water. So when you drink the stuff, if you can tolerate it, it doesn't taste great, but you can add a few things to it to make it palatable. And you drink it, you're directly drinking easy water. And so in some way, that easy water is then, in some way, it contains negative charge. And the negative charge, I believe, negative charge can flow very easily from the water that you drink, can flow very easily throughout your body, seeking regions that are less negatively charged, or you might say more positively charged, because negative always wants to go to positive. So any of your cells that don't have, that are insufficiently negative, that negative charge will flow in. And we found in the laboratory, you simply add negative charge and it to water, and it converts it into easy water. There's another way to build easy water. So I've gone through a long explanation, but basically drinking the stuff from your garden, the water from your garden, getting rid of the bulky stuff so your stomach doesn't get very full very quickly and you don't stop, and you drink this water, it provides the electrons that are necessary for the buildup of easy water in your cells. And I'm not sure what your experience is, but I've heard from various health practitioners, one sort or another, that this seems to be like the best expedient for improving your health. Okay, that's 2. Another one is sunshine. So going out in the sun. So, mostly we think of the sun as giving light, and of course it does, but roughly 50% of the sun's energy is in the infrared region. That's why it feels warm in the sun. It gives off infrared energy. And if we're exposed to it, then we can receive that massive amount of infrared energy. And so in Seattle, where I live, and not where you live, but it's cloudy a lot in the wintertime, and when the sun pokes through the clouds, you can see smiles on people's faces. So why is that? Well, so the usual reason given is suddenly the light appears, we feel good, it's a psychological effect, and it may well be. But I think it's also a physical effect, because when the sun comes out, and shines on us in one way or another, it provides massive amounts of infrared energy. And that infrared energy can penetrate to our brain. The evidence for that is you can take an infrared source and put it here. It passes through the skull, gets scattered by your brain, and then some of it goes back through the skull. It's picked up by a sensor. You can image the brain that way. So if you can image the brain, it means the original energy must be getting through your skull twice, actually. So that's another, excuse me, my hair is getting in my eyes. That's another expedient, or another way that you can you feel good, because your brain, because the cells in your brain, the nerve cells, I guess in your brain, might have been deficient of easy water. And the fact that the sun comes out, it means they're going to build easy water, and your cells return to their, shall we say, default state, that is feeling good, we're designed to feel good, not to feel down and sad and depressed. And so the sun comes out, we feel good. I think that could be contributing. So that's I guess a third. Fourth one is the sauna, or as the Finns say, sauna. So I had experiences both in Finland and also in Russia where they call it banya, and it's a little bit different, but the main features of a sauna are heat, and heat, as I mentioned, is associated with infrared. So you're receiving massive amounts of infrared energy, and you go into the sauna and or banya, and you come out and you feel like $1 million, right? Or at least much of the time or most of the time. And I had that experience myself. I was in Finland giving a talk, and it was terrible jet lag. And they said, there's a party we're having outside the town or city. And they took us to the party, and there was entertainment and music. And all I wanted to do was put my head on my pillow and sleep. And at 10 p.m., the host got up to the microphone, and I thought for sure he's announcing, okay, it's time to get back on the bus, and we're going to take you back to your hotel. Well, that's not what he said. He said, okay, it's time for the sauna now. And um, he was describing three different kinds. One is dry, one is wet, and there was another kind. And he said, after it's over, you're free to jump into the water, cold water, and get refreshed. I didn't do that, but I went to one of the saunas, and I was just feeling so tired. And when I came out after a shower and such, it was like the beginning. I had had 8 hours sleep, and I was ready to go again, even though 30 minutes before that, all I wanted to do was sleep. So I had that kind of experience, and the same in Russia. Um, the Russian ones are a little bit different. After you get, maybe you've had the experience, they beat you with the leaves of a birch tree. You've had that experience?
Yep, yep.
Okay. Yeah. Anyway, that was pretty exciting. So um, yeah. Anyway, so that's the fourth experience, sauna. And as you know better than I know, you can get portable electrical saunas, just infrared lights, basically, that do, I guess, much the same thing. But it's nice to enjoy the original. Okay,
Mhm.
that's four. Um, fifth one, fifth expedient in promoting health, and all of these are as simple. Um, is to eat the right kind of herbs, spices, what have you, and starting back from Ayurvedic times, 5,000, 10,000 years ago. Of course, people were equally interested in their health as they are today, and it became clear that certain herbs were good for health. And one of them, for example, is turmeric, which is widely advertised now. Um, and with modern allopathic medicine, we've forgotten that some of these substances can be good for health. And so we began wondering why turmeric, basil, so-called holy basil, ghee, why are all these so good for health? And you could imagine, if you were oriented toward allopathic medicine, orthodox thinking, you might say that, oh, there are receptors for ghee or whatever, or turmeric all over your body. You've got receptors in your heart, and you've got receptors in your liver, and you've got receptors to the receptors. And that's one. And that one is a possibility, though it's a bit complicated. The simpler one is that the water that's in every one of your cells is subject to the influence of these special herbs. And so we started thinking, well, maybe the reason that turmeric is so good for so many different issues that may impact you, the reason that's the case is it builds easy water, and easy water is all over. And so, maybe that's it. And we tested it, and we published the result, and the result was uniform, that all half dozen or so of the herbs and other substances that we test that are known to be good for almost no matter what ails you, they build easy water. And that's why they're good for you. So the conclusion is, if you want to remain healthy, and we published all this stuff. It's good to take moderate doses, if you will, or amounts of some of these herbs. They really do work because they build easy water, and easy water is critical for health and function. So that's another really easy expedient that I myself don't do enough of, but I should. Okay, sixth one. The sixth one is grounding or earthing. So we don't, as a rule, we don't connect ourselves to the earth because we wear shoes all the time, and the shoes have leather, which is insulating. But it's become well known that if you take off your shoes and connect yourself electrically to the earth, you feel better. And there are all kinds of theories because it's known now that it really works. You can either walk on wet grass, or you can hug a tree, or you can walk on sand near the ocean, damp sand, or you can bathe yourself in a mud bath or whatever. In all these cases, excuse me, you're connecting yourself to the earth. So why should that work? Well, so the reason I think that it works is actually quite simple. Excuse me. And that is, the earth is negatively charged. And if you connect yourself electrically, you pull in this negative charge. Now, I must admit that I was educated in electrical engineering. Never, ever did any professor even hint to me that the earth might be negatively charged. We were taught that if you got a plug, a three-prong plug, you have that extra round plug, and you plug into a receptacle, you're connecting yourself to a bland sea of neutrality. That's ground. That's what we learned. And I never heard even a hint to the opposite. But I found out that's not true. I found that the earth is negatively charged. And I found out from a Russian guy who was working in my laboratory. And this guy was full of ideas. And sometimes I didn't have the patience to listen to all of his ideas. But the day he was leaving, he starts telling me, expounding on the electric field of the earth. I said, Andre, you mean magnetic field, right? I never heard of electric field, and I was schooled in electrical engineering. He said, oh, you didn't know that the earth has an electric field? I said, what are you talking about? You're nuts. He said, no, I mean, the ionosphere is positive and the earth is negative, and it's like plates of a capacitor. And in between those, you've got electric field lines running perpendicular to those surfaces. And the bottom electrode is the earth. It's negatively charged. I said, I never heard of such a thing. You're crazy. And Andre said, I promise you, every middle school student in Russia knows that the earth is negatively charged. I found out later that is actually true because I know some senior scientists who come from Russia, and they said, yeah, they learned that in middle school. So he said, there must be something deficient with the educational system in your country. And I said, well, yeah, I must say, I do agree with that. So I went home with my head spinning. Is he right? Is it possible that he's right? Next morning, one of my students who was overhearing the conversation brought to me the famous lectures of Richard Feynman. Feynman, was a Nobel physicist who many people think of as the Einstein of the second half of the last century. And he brings to me, and opens volume 2, chapter 9, and it's all about evidence for the negative charge of the earth. And after I read that, I was convinced because there was ample evidence. It's just that, we don't teach it. People don't understand that the earth has a net negative charge. To this day, it's not taught, but to me, it turns out in some of the subsequent work that I've been doing that not only is the negative charge of the earth interesting, but it's critically important for so many different phenomena. And if we don't recognize that it exists, we're going to go off on the wrong foundation. Because so closing the loop, what happens if you connect yourself to the earth electrically? What happens is all those negative charges that are in there will sweep into your body, and any regions that are short, deficient of EZ will get filled with electrons and build EZ. And that's why if you earth yourself or ground yourself, you feel better. I think that's the explanation. There are many explanations you'll find throughout the literature. I think this is the one that makes a lot of sense to me. So those are 6 expedients that are not difficult to do and can improve your health. And just before I stop, there's a 6th one that I need to mention. I guess I don't put it in the category of the simplest, but it's really important, and that is hyperbaric oxygen therapy, which I've had and my late wife had for various reasons. And what is that? So it's a kind of chamber where there's higher than usual pressure and higher than usual oxygen, hyperbaric, high pressure. So you're breathing almost pure oxygen and at high pressure. And again, we wondered why it has such positive effects on so many different syndromes. And we indeed found and published a paper showing that high pressure builds EZ and high oxygen builds EZ. So you put the two together and it's a powerful builder of EZ. So I hesitate to mention it because, it's not so easy to get one of these chambers. You have to go to a medical practitioner who has the chamber, and there are many of them around, but they're really effective. So anyway, I hope I've answered your questions about, how you can build EZ water in your cells, in your body, and thereby improve health.
No, you did a perfect job. And it's so interesting because so many of the things I recommend to patients, from hyperbaric to infrared sauna, and juicing and everything else, right? But this really explains on a deeper level what's really going on inside their body and inside their cells and why they're feeling good too during this time.
I'm pleased, but not surprised that you recommend all that because it does seem to work. And so
Right, it really does.
I bet your clients are really happy dealing with you.
So I have an interesting question though with the spices though. So if they're dried spices without water and you take them into your body, or let's say like tea, dried herbs, does it have the same effect as like a fresh plant on your cells to make easy?
Um, I uh, I'm not sure of that. I'm trying to think through. Uh, the herb itself. Um, if you put it in water, either some of them will dissolve, some of them don't dissolve. But if it doesn't dissolve, it builds easy water around it. So um, I guess uh, 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 I'm not really sure which one would be more potent. Maybe you have some idea about your patients and which ones, what they actually take and which ones are best for them and which ones not as good. Do you know that or?
I'm not sure. I mean, I always look at tea as like a more subtle form to give nutrients versus different extracts or things like that. And so maybe it's a more subtle way as it dissolves in water versus like the whole plant or juicing the plant and taking the fresh nutrients. I don't know. I don't
Yeah,
know.
I
It's
don't know either,
interesting.
but it's a really good question and it's worthwhile studying. We haven't gotten to that, just so many things that we can do in the lab.
Right.
The very modest funding that we have, it's really difficult to get money to study unorthodox stuff. Um, so that's
Right.
another topic, but I'd rather rather than expounding on that, I'd rather listen to your questions and see how best I can answer them if I can.
So the next question I have kind of moves into like, can you tell us more about how water can store information and how we could utilize this potential benefit for our own healing?
Oh, that's a great question. That's a great question. So I've been intimate with that subject for quite a while. And I guess that the most famous person in that field is Masaru Emoto, uh, who passed almost 10 years ago, and there's going to be a memorial ceremony for him, in which I'm going to be speaking. And for those of your listeners who don't know his work, he was a spiritualist. People call him a scientist, but he was actually more of a spiritualist. And he discovered that if he would project his energy on water, it would impact the water. So the way he did it is he would project positive energy or negative energy to contrast the two. And if the energy was positive, like he would either say, I love you to the water or think positive thoughts to the water, then it would freeze the water and you get beautiful crystals. If he thought, I hate you, or you're ugly, or something like this, he would freeze the water. He got ugly crystals. And that made a big hit with a lot of people, and his book sold millions of copies. And and I know the Emoto people very well. Um, but one of the problems that scientists object to in that is, it seemed that water has a kind of memory, or it can store information, but he would project the same energy to 50 different containers of water, and of the 50, he'd look at them and he'd pick out the one that best illustrated what he wanted to demonstrate. Scientists don't do that. They'll randomly choose 3 or 4 from the 50, and let's look at them and analyze them. Um, so people who are in the know scientifically uniformly reject his work, but other people really like his work, and I must admit that right now there's a woman, her name is Veda Austin, and she's gone on to produce work that is not exactly the same as Emoto, but somewhat different. She typically will ask you to, example, to think about something, and then puts the water in the freezer. And she did it actually in my home, but she's since become very well known with followers. She puts it in the freezer for 10 minutes. And so there's just a thin film of ice at the top. And in my case, I was thinking about a house, and she pulled it out after 10 minutes, and I could see the roof of a house on it. And she demonstrates on her website that she'll take some water and she'll write the number 4 and place it either on top or beneath the chamber, freezes the chamber, and in the thin layer of ice, you can see the number 4 that's written. So amazing. And she'll be speaking at our water conference, which, by the way, anybody is welcome to attend. It'll be held in Lisbon in October, the middle of October, 16th through the 19th. If anybody is interested, it's called the URL. It's called WaterConf, WaterConf, nothing in between, for conference, waterconf.org, not .com, waterconf.org. And we're happy to see you there. And so I mentioned that not only because she's going to be there and demonstrating what she does, which is really fascinating, but also we used to have Luc Montagnier, Nobel laureate, discovered HIV. He used to come. He came every year for a decade. Unfortunately, he passed last year, and he would present evidence for water memory. And before him, I'll tell you about his experiments in a moment. And before him was Jacques Benveniste, and he was perhaps most famous for demonstrating information or memory in water. And I'll just briefly tell you his story because it shows what happens when people deviate a lot from the mainstream. So Jacques, whom I knew, he's passed. He was studying the effect of some antibodies on various cells. What were the cells? I forget for the moment. Anyway, the cells, he would expose the cells to these antibodies, and a very specific reaction took place, and the cells would basophils they were called. They would secrete, I think, histamine. Um, and he was doing these experiments, and he was a famous scientist, high-level scientist in France. And someone came along and said, well, I can achieve the same thing in homeopathically diluted antibodies. So you take the antibodies, he would dilute them by 10 times, shake it the usual way, and then dilute it again 10 times, and so on, many, many times dilution. And therefore, according to common belief, all you have left is water. And he said, I can take this water, which has information, he said, from the original solution or suspension, and I can take that water instead of what you use and expose it, pour it on those cells, and the cells would secrete. And he said, it's impossible. Water is not, this is a very specific reaction. Water is no way to do it. But on the other hand, there's an empty space in my laboratory, parenthesis, containing 50 people approximately, high-level scientists, and demonstrated. And before long, everybody was huddled in that corner around this guy because it worked. He could show that homeopathically diluted result could achieve the same thing. And the homeopaths were excited about that because here was this famous scientist, who's demonstrating that the homeopathy really does have some meaning to it, which a lot of people, and even to this day, are highly skeptical. So Jacques Benveniste took the demonstration and started doing his own experiments, and then sent it to the journal Nature to publish. And the editor of the journal, Sir John Maddox, sent back a letter. All of this is publicly available, all this, what I'm telling you about. And he said, I'm refusing to publish this article. You're a distinguished scientist, but I'm afraid you're wrong. You have to be wrong, because if you're right, then everybody else is wrong. And I can't believe that everybody else is wrong. So it seemed that Jacques was defeated, but Jacques was not the kind of guy who was easily defeated. So he asked colleagues of his, a half dozen colleagues from around the world, to repeat his experiments exactly and see what they came up with. And they all came up with positive results. They could get the same effect that he saw. And so they resubmitted the paper, and the response that came back was pretty much the same. I don't care how many people repeat it, it can't be right. And that, Sir John Maddox, when he passed finally, they couldn't get too many people to speak favorably of him at his funeral or at his memorial service. He was that kind of guy. So, and then after that, the homeopaths in Paris, where he was working, they objected because, hey, this famous scientist is demonstrating that what we do really is real. It makes sense. And Nature is located in London, so very quickly it got from Paris to London, and they were feeling under pressure. So they sent they called Jacques, and he told me, he said, see that red phone over there? I got a call from John Maddox. And Maddox said, I'll make a deal with you. I'll publish your work in the next issue of Nature, the most prestigious science journal, Nature and Science. And on the one condition, and the condition is, we'll send a commission of your peers to look over your shoulder, see what you're doing, and then we'll report back to those readers a few weeks later. Will you accept that? And being maybe beautifully naive, Jacques said, of course. He didn't realize that this was a setup. And the story I'm telling you, you can read in many, many different places, but it's such an interesting story, a sad story in a way. So Jacques said, sure, no problem. He was confident, even though he said in the paper that finally got published, is that this works not every time, but almost every time, enough to be easily to pass statistical significance, but occasionally it doesn't work. So they published the paper, And they set up a committee of people to come and visit the laboratory, the foreign visitors. And the committee consisted of three people. Maddox himself, who had, an axe to grind. Um, Next one was a guy named Walter Stewart. And Walter Stewart was working an American working in the National Institutes of Health. They had just recently built a Center for Scientific Integrity, and he was working there. And the idea is, if you were cheating in some way, he would go to investigate and find out if you were guilty or not guilty, in theory, an objective person. And if you were guilty, then you could never receive another NIH grant or other more serious consequences. Because, people historically, someone will say, hey, my rabbit, because of XYZ procedure, it's a white rabbit that has a black spot on it all the time on its thigh. And someone would come in and say, well, I saw him coming in at 4 a.m. and painting black spots on the rabbits. So it didn't occur naturally. It was cheating. And they would come to investigate. Anyway, this was the second guy, and they were obviously suspecting that they might be some cheating going on there, because they were sure that it couldn't be true. So he was the second one, that was Walter Stewart. And the third was James Randi, better known as the Amazing Randi, a magician, and a famous magician at that, not a musician, magician. And he was famous for being able to uncover the tricks of other magicians. So very talented guy, but ethically speaking, he wound up offering a prize of $1 million for anybody who could demonstrate water memory. He would be the judge himself. So
That's convenient.
yeah, so you got three people who were coming, and it was like a commando group coming to your laboratory. And so they reproduced the experiment the first day. The first day, everything worked exactly as reported. The second day, they changed the routine a little bit. Everything worked exactly as reported. And the third day, it was Walter Stewart, the second one I mentioned, who did the experiment, and it almost worked, but didn't work. And they said that sometimes it doesn't work. And parenthetically, it was that when there's a disbeliever there who does the experiment, it doesn't work. There's more on that, but that sit for the moment. So they huddled in their hotel room and they said, hey, it looks like when the French scientists do the dilutions and the experiment, it works. When we do it, it doesn't work. That is n equals one attempt. And so they went home, and the editor wrote a piece that they published and said, water memory is a, quote, delusion, a trick. And from then on, Benvenist's career took a plunge. He was considered non-serious, and there were jokes, hey, you're having trouble remembering? Drink some of Benvenist's water. It has memory to it, so your memory will improve. That sort of thing. He became a scientific joke. He became depressed. Nobody would listen to him, and he died prematurely, unfortunately. So I know various other people who were involved with that. So that, anyway, I'm saying this because he was really the first person to do serious experiments on water memory. And when he died, he had been a friend of Luc Montagnier, the guy I mentioned who came to the Nobel laureate. So he started taking up experiments where Jacques Benveniste left off. And he presented his experiments. And, when you hear from a Nobel laureate, you kind of take it seriously, even though Jacques Benveniste was perhaps equally prominent. But so Luc would do the experiments, and he reported at our conference. And I'll just tell you briefly what he did, because it's so interesting. So he took two sealed containers. He put them near each other. The first one had DNA in an aqueous buffer, that is water with some other ingredients. And this is pure water. And both are absolutely tightly sealed, so there's no possibility of chemical communication. And he said, this short sequence of DNA, the sequence would be transmitted somehow to this water. He didn't say how, but there's some maybe an electromagnetic kind of signal or some kind of unknown energy. Um, and then he took this, threw it away. So he's got the water that he hypothesized has all the information, either from the DNA, from the sequence, or from the water surrounding the DNA, because he often used seriously diluted DNA. Um, and and he tested this with the PCR method, the one that's used for COVID, and he found indeed that the sequence of the DNA that was produced from this water and all the precursors that you need was the same as the original the water had been sitting next to. So hardly believed by anybody, because this is too astounding if true. On the other hand, it's now been repeated and published by 3 different groups. And if you're willing to take a repetition by independent scientists as a sign of truth, and it's a sign of truth. So Luke was at our conference. He was very happy because we like to hear interesting stuff like this. On the other hand, people began to hate him for not only that, but because of his political views, antivirus views, which were not really antivirus, but coming with the idea that if there's a danger that, and he was a physician to start with, and so he was one of the leaders in the anti well, antivirus movement. And so a lot of people discredited him for that. But and then unfortunately he passed. So I'm giving you this information because you asked me about water memory. So Jacques Benveniste produced clear evidence of that has in fact been reproduced in many laboratories since then. So and Luc Montagnier, Nobel laureate, produced evidence that has been reproduced in other laboratories. And each year at this conference, we have other people who come and use different techniques and demonstrate that water has the capacity to store information and has a memory. And we ourselves are now engaged in studying whether this is the case or not. We haven't serious results yet, but we're working on it. We take water, and we have a healer who comes to the laboratory, projects his or her energy on the water, and we compare the physical chemical properties before and after to see if there's some difference in the water. So we have no serious results yet, but we're embarking on that. So we'll see if that's the case. But in our conference, Lisbon, I said this year, almost everybody who attends is open to that point of view that water may indeed have store information or receive the energy from information-based energy in the water. And because the evidence is there, it's just that a lot of people are not willing to pay attention to it. But the reason I think it's possible that the information is stored in EZ water. See, ordinary water has randomly oriented molecules bouncing around. You wouldn't expect any kind of information to be stored in a system like that that's moving around on a femtosecond time scale, and randomly oriented. But EZ water is different. It has structure to it. And if you compare the structure of EZ water, where you have regularly disposed oxygens and hydrogens forming those hexagons, they're ordered in 2 dimensions, and those stacks are ordered too. So they're ordered in 3 dimensions. It's almost the same as a computer memory. So if you think about how, if you got a thumb drive, you're using it to store information, you stick into your laptop, what is it? Well, it's basically a planar structure that has transistors that are packed in it, regularly disposed in 2 dimensions. And each one of the transistors can be on or off or 0 or 1. And it's the array of zeros and ones that stores the information. Well, the easy is much the same, except it's a three-dimensional array, not a two-dimensional, which gives you another dimension of information. And it has oxygens and hydrogens. And the oxygens um, are known to have not two, but five different oxidation states or charge states. The one that we think of most frequently that we learn in school, in high school, I guess, -2. That's the so-called valence. But oxygen can be not only -2, but it can be -1, 0, +1, or +2. And you can read about that in any chemistry textbook. It's not arcane information, but it can have all of those charge states. So if you think about the EZ array, it's got entities and regularly disposed entities, the oxygens, that can take on different states, not just two, but five. And you've got it in 3 dimensions instead of 2. And everything, so it has should have the capacity to store information. It's very similar to, to the computer memory in that sense. And because the structures are at an atomic level rather than a transistor level, it means they're really packed tightly. And we made a calculation. If the EZ really works the way we think it might work, it's packed so tightly that the information density is something I think we computed like 1 billion times the density that we have now. So we now have, a pretty small drive or thumb drive that we can put in, but in the future, if we're right about this, then a computer could be the size of a pinhead. And
Wow.
yeah, so you asked a short question, I gave a long answer, and to summarize, the answer is that there's a lot of information supporting the idea that water can store information beyond Emoto and his stuff, which is so interesting. And the principle of storage, I think it lies in the structure of easy water. So we're looking forward to in the future, one of the things that we would like to develop if we ever get money to support our work and pursuing this is to actually do what's necessary to develop a memory system, a usable memory system that's based on easy water. And we can imagine, we can now produce easy water that's in gel form, in solid form, actually. This was originally found by an Italian group, and we produced their work. And so we can take easy water and convert it into a solid. You could powder, and all you need is add water and the easy is restored. So we can put that into the computer memory, and that, you can imagine putting powder or something into a device rather than a gel into a device. So it may even be practical. Okay, I think I need to shut up
Right.
and wait for your other questions.
Well, I think what you've explained to our audience so far is pretty amazing of what water can do and how to look at the substance, that not just a substance that's in our bodies and just part of us. It has real healing power on all levels, and the potentials for what we can do, whether it's information storage and everything within us too, and utilizing that to heal ourselves. I think the potential is endless if
Well,
we get
thank
the
you.
information out.
I'm really excited about it. There's so much more to be done, and the limiting factor actually is funding. It's really hard to you submit an application to a granting agency, and if the reviewers, first of all, if they don't know about easy water, they don't have the time to like read the book or look in the literature, and so it's easy for them to put that at the bottom of the pile. And also the idea that if they do know about it, they're being challenged.
Right.
They don't like to be challenged. They don't like their toes. Their toes are fragile. They don't
Hmm.
want to be stepped on. And so the only way that we've been able recently to get money is through private donors. And and we had a donor who read my fourth phase book, Fourth Phase of Water, and he sent an emissary to me to have lunch with me to find out if I was an okay guy. he liked the book, he liked the contents, he loved the contents, but he didn't know me. So so this guy, it wasn't an interview exactly, but we sat down over lunch and we had a lot of discussions, and we shared a lot of the same visions. And he reported back to the billionaire guy, he's okay. And so soon after we got very, very nice funding from him, but unfortunately, after a few years, he continued to love what we were producing, but he said he ran into a financial problem that his assets now were mostly or almost exclusively tied into very large investments that he couldn't easily convert into cash. And so he gave me a year's notice, and he had to stop. And he's helping to look around for people who might be able to be in a position to fund us. So we're really, it's a statement about the scientific system, and it's pervaded history. If you do something that challenges the mainstream thinking, there are consequences. And for us, the main consequences are trying to get funding. And so our laboratory is it's operating nicely, but not at full speed. And so we look forward to finding people who who have done well and want to contribute some way to science in a meaningful way. And so we're trying to find such supporters. Anyway, I thought I would mention that because it is a limiting factor. There are so many things, and
Mm-hmm.
many of the things you mentioned that we'd like to do, but if you don't have the people to carry out the experiments, you can't do them.
Right.
So
And I think getting that information out there is important too, because then the right people will find it.
I think so. I hope so.
Okay, I have one more question for you because
Okay.
I know we're running out on time, and this one's a little different because I was reading somewhere, listening that your next book is on the structure of the atom, and you come up with an alternative model to that.
Yep.
Can you tell us a little bit about that as we're kind of questioning everything that we think of as kind of the foundation, whether it's cell energy or muscle?
Absolutely. This subject is dear to my heart, and as you're suggesting, if you build on a foundation that's wrong, it's got cracks in it. Every structure that you build on that foundation will be erroneous.
Mhm.
And Unfortunately, I guess I really do feel that way. Okay, so think about the atom. This is not complicated stuff. So what does the atom consist of? It consists of a nucleus, and it consists of electrons or electron clouds that surround the nucleus. Uh, and even though the model has been amended again and again and again by quantum mechanical considerations, still that essence remains. There's still a nucleus, and it's got neutrons and protons and electrons in various orbitals around it, uh, and they're negatively charged. And so the nucleus is positively charged because it's got neutrons, which are neutral, and it's got protons, which are positive. And protons want to repel each other. And if you put them very close to one another, the repulsive force becomes huge. The closer they get, the bigger the force. It's an inverse square relationship. So you try to take. It's like pushing two north poles of two magnets together. We don't want to be that way. So it's like in spades in the nucleus, because some of the heavier atoms, you're sticking together numerous protons right next to one another, pretty much. So when you think about it, what do you expect to happen? Well, the nucleus will explode, right? But you can't have a stable atom when the nucleus explodes. And so the physicists actually thought about that, and they invented something to remedy the problem. So what's the remedy? Well, the remedy is something called the strong force. So the physicist said there must be, since we know that that model is correct, um, all the physicists were ready to accept it. There's got to be something to hold together the nucleus, and they invented something called the strong force. As far as I've ever been able to see, there's no independent evidence of a strong force. It's a kind of glue that does nothing but hold the nucleus together and thwarting its tendency to explode. Uh, so this is one problem, but it's not the main problem. This is just one. You can't have nuclei exploding, otherwise it would be a so-called nuclear explosion. um, okay, second problem. I learned in middle school, or it was called junior high at the time, and you learned too, that positive charge and negative charge attract each other, right? So think about it. The nucleus is positive, but all those electrons are negative. They attract one another, right? And so you can imagine the consequence of that. That is, the atom will contract to nothing. All these electrons would coalesce on the nucleus, and you have no atom left. You have just a spot left, a tiny spot. So you've got two basic problems. One is the problem of that the nucleus will want to explode unless you invent something to prevent it, and the electrons will want to collapse onto the nucleus, and you've got no atom left. So the construct is unstable. But there's more. You know, suppose you're a random electron that comes into an atom, right? And first thing is you have to figure out there are orbitals. This is part of the theory. The first one has 2 electrons, the next one has 8, and so on. And you got to figure out, you're in theory, you're supposed to land on one of these orbitals, and you got to figure out whether the orbital has 7 or 8. Because if it has 7, yeah, you want to land there, or it says you should be landing there. But if it has 8, you can't. How are you going to figure that out? You're an electron. And also, since you're an electron, you repel other electrons. And the last thing you want to do is join one of those orbitals with other electron neighbors nearby, where you prefer to sit in between the orbitals, but that's not allowed in the model. See, so you've got a problem there. Finally, there are more, but most atoms at room temperature, they form solids. So my laptop sitting here is, I think it's aluminum. So you take 2 aluminum atoms, in order to get a solid, I should say 90% of atoms in the periodic table at room temperature, they form solids, which means the atoms need to stick to one another. Otherwise, you can't get a solid, right? So I'm giving aluminum as an example. 2 aluminum atoms, they need to have a strong tendency to stick together to form a solid. Now think about it. The outer shell here is electrons, and the outer shell here is electrons. You bring these 2 atoms together, they don't want to join one another. They want to repel each other. And so how are they going to form a solid? And the chemistry textbook says something about sharing electrons, but I could never figure out how sharing electrons solves this problem. So I mean, it's a real problem. So there's a multitude of very simple problems that impact the theory of this. On the other hand, you know, the model's been around for 5 or 6 generations. Yeah, well, it was the early 1900s. And, you know, typically we think if it's been in the textbooks for 5 generations, there's no question that it must be right. And we presume, most of us presume, that it must be right. But if it's right, you need to address these fundamental problems. And therefore, I think it's not right. And I think we've been deluded into thinking that it's right. And we've built so much of science on the pretext or the presumption that it must be right. But it leads to mechanisms that are very complicated. And usually, you know, if we take Occam's razor principle, that you've got 2 ideas and the simpler one is likely to prevail. And that's pervaded science for ever since Newton thought it was a good idea to take this theological idea originally from Sir William of Ockham and translate it into a scientific paradigm or way of thinking. Everybody believed it until about 100 years ago with the advent of quantum mechanics. And quantum mechanics, nobody can understand because there's no understanding. It's pure abstract mathematics. So if you're expert in mathematics, you can deal with quantum mechanics. If you're not expert, you have to rely on all those smart physicists who you presume they know what they're talking about, they know what they're doing, and they're dealing with the intricacies of quantum mechanics as amendments to the structure of the atom. And there are some observations to speak for the positivity of quantum mechanics, but there are others that say, no, this is that Mother Nature doesn't operate with abstract mathematics. Mother Nature operates on simple principles. And I guess I'm a believer in the simple principle idea. So the atom, even as amended, modified, still we have the same basic construct of a nucleus and electrons. And for the reasons I spoke to and others, doesn't work. So something else has to work. And the book, first of all, describes the problems, and then it describes something else. And I think the something else is primarily a cubic structure of atom. You know, if you have cubic structures, you can put two of them together nicely and join them without any intervening space. If you take two spheres, like the current idea, and you try to bring them together, they meet at one point. The rest of it is open space. What's in the open space? You know, nobody has been talking about the open space. But the cubic model explains that. It explains how you're able to stick two atoms together. You know, if you have positive charge, I'm simplifying, positive charge on this face, negative charge, they stick together very easily, and they'll maintain their stickiness. So the book spends a few chapters describing how this simple model can explain many features of modern physics and chemistry in very simple ways. And what I discovered, this is the final point, I'm sorry, going on and on, but what I discovered after I'd written a draft of this book, and like other books that I'm in the process of producing, and my son is the artist, and he decided to take 3.5 years to remodel his home because his family is growing, which means I have no artist for 3.5 years, which means I can draft books, you know, and they're just waiting in line. So a book is coming out soon about the effect of electrical charge in nature. And then the atom book is the next one, but it's been waiting there. And so some he's a great artist, and some illustrations need to be, but you know, I think this book is or what I was going to say is, I discovered after the book was written that the same idea came from one of the most famous chemists 100 years ago. I was actually not thinking that, oh, I'm just repeating what this guy did, because I found it independently. I came to the same idea. But if you know the history, which most people don't know, you know, it was the era of physics. The previous century was the era of chemistry. But with Einstein and Niels Bohr and other Max Planck and who came, it became to be the era of physics. And so physics dominated the scene. And Niels Bohr, who was the architect of this structure, he was ultra famous and distinguished. So since it was the era of physics, the physicists liked this particular idea, the so-called solar system model, and then they went on to modify it with quantum mechanics. But the chemists hated it. And so the two most famous chemists of the day, G.N. Lewis and Irving Langmuir, who are legends in the field of chemistry, and they said, this is nonsense. And I found something from Lewis in one of his notebooks. It shows the structure of different atoms with cubical shapes, with electrons at the corner. It's not exactly the same as I'm suggesting, but the idea is so similar that I found myself extremely gratified to see that among the most famous chemists of the day, who rejected the physics model, saying it just doesn't explain the simplest of chemical reactions, you know, so it can't be right. So that gave me a boost of energy. Anyway, I'm looking forward to the publication. I know that among physicists it will not be well received, but that's okay. I have to put forth what I think is maybe close to the truth. So I'm sorry for my long-winded answers to your short questions.
Well, that was an intense question, especially to end with, but I think everything you've given today will help people question things and question kind of things that they might have taken for granted or just believed because that was what it was, rather than what really science is, which is questioning, stepping back and not attaching to the what we know and saying, is this right? Does this make sense? So I think you brought a lot of great points too.
Well,
And
thank you for that, and I fully agree with you. I think that's probably the most important take-home message. What you read in the textbook is not necessarily right.
mhm.
Uh,
Yeah, so having the ability to question it and the courage to speak out or say something about it, even though most people don't really want to hear
no, most people
hear
don't
the
want to
other
hear it.
side. That's the other thing.
That's
Yeah.
right. Yeah, we feel comfortable in the sort of sphere of understanding that we have, that we learned, that we thought about. If someone says, "Oh, that balloon has a hole in it," it doesn't sit right mostly. It's
Hmm.
too bad because I think that we need to change the system. The system needs serious change because it doesn't produce scientific revolutions. We need scientific revolutions to improve our world. The world has so many problems, and usually, if you have a scientific revolution, almost always there's some new technology that comes out of it you could never even dream of before that revolution. Like, for example, discovering at Bell Laboratories 80 or 90 years ago, semiconductors. Who would ever have thought that semiconductors could lead to laptops and Zoom communications? Uh,
Hmm.
but that's what happened. And and other similar discoveries, they lead to technological applications, and those applications can do a lot for our society, especially now that we have so many societal problems that need solution. And some of them obviously will be solved through hopefully solved through political means. But other than that, scientific input into that can solve some of the or even most serious problems, like getting drinkable water, getting energy. Those are
Hmm.
all into the realm of science. Yet, there can be wars over water, and I think there already
Hmm.
are to some extent getting water. So yes, the most important take-home message I think, is retain an open mind. If something doesn't make sense to you, it doesn't mean that you're stupid. It may mean that the idea doesn't have any merit at all. It's just humans
Exactly.
that invent these ideas, and we all pee in the same pot. So there we go. Uh,
Exactly.
okay, I hope that does it. Our readers.
Yes. Thank you so much for coming on today and sharing everything with our readers. I greatly
My
appreciate it.
pleasure, and thanks for those great questions. Okay,
Okay.
take
Thank
care.
you.
Okay.
Bye.